Okay, so thus far, we've seen a lot of tools, the basic tools that we can work with. But there's one more that's considered a basic tool, and it kind of makes our lives a whole lot easier. So let's take, for example, a payroll calculator. Maybe we've got just 3 employees. That would be a start. And we need to save their data with what we've seen so far, save their data into variables, then process through it. So we're going to have like employee 1 name. Then we have other stuff about the employee 1. So like employee 1 rate of pay. Probably have to have other information about them to write a paycheck. So employee 1 address. And that can go on, but however much data we need about each employee, we're going to put each piece of data into a variable to store and work with it. But maybe if we have a couple employees, that pattern needs to continue. So we'd have like employee 2 name, employee 2 at pay, how much they get, how much they make each hour, employee 2 address. And this pattern is going to just keep continuing. Employee 3 name, employee 3 pay, and it's just going to keep going on for however many employees we have. So it would be nice if we could consolidate this information and maybe put all of the names in one collection so that we can work with everybody's name at once. Or maybe put all of the information about employee 1 into some collection of all that data instead of 3 separate pieces of data. So that's what we're going to look at tonight. We're going to be looking at collections. And I'm going to put in quote marks arrays. That's typically what we'll say. We'll just give the word array, but there's a point about that we'll talk about here in just a moment. So I need a little bit of room, so I'm going to erase this section of the board. That was just kind of a lead-in example, just showing that if we store everything as single pieces of data, we're going to need a whole lot of variables to hold every single piece of data we might work with. Yeah, I'll go ahead and erase that. And we can consolidate that by working in collections, like I was saying, put everything about employee 1 into one variable, or everything about all the names into one collection, and then work with all the names at once and all the rates of pay at once, and consolidate all our data using arrays. I'm going to draw a couple of pictures here. Back to the stack heap diagrams to kind of look at what's going on. So with that first example, I'll abbreviate this. We had all sorts of different blocks of data over here to work with, maybe scattered all over memory. And however many there were in there, then I just erase off the board. So it's kind of scattered all over memory, lots of different things that we can work with. The idea of an array is really just to consolidate all those. So instead of lots of different chunks of memory, we just build one big collection of memory. Put up at like 5 in each one. So 20 things, 3, 4, 5, 6, 7, 8, 9. So the idea is then in our code, we just have one reference pointing to all that data, and then we'll kind of split it up into little chunks in here. something like that. So we still have the same data, it's just consolidated into one place. And one of the big things to notice is the reason, main thing we're going to want to think about at this level is over here, instead of having all those different variable names to keep track of, we only have one reference to keep track of all that data with. And that's what an array is, the idea of an array. Everybody should have seen these in SDEV 120, so we'll go over this kind of quick and get into examples really quick here tonight. And there's some other things to keep in mind, like storage and stuff, but that's kind of later. I made a note about it, but at this point, we're mostly just we want to be somewhat aware of that. But for those who progress further in programming, you'll want to, as you progress further, you'll keep that in mind and look more and more in depth at what's going on in the background and what we can do to improve that. So now kind of getting into collections. And I started with this word up here in quote marks because we're doing everything in Python this semester, or most everything in Python. And in Python, we don't use arrays. So the actual definition of an array is, I think I wrote it down here. Did I write it down? I'm not sure what page it's on in the notes. I have it written down somewhere, but it's data of similar type stored and retrieved via a recursive algorithm. So the picture I drew here kind of showed them all together. That's a way to think about it. We could have an array scattered around like this. What's important to retrieving it is that it's a recursive algorithm. So maybe our first piece of data on here is like a bit, I don't know, 845 is our start. And then the next piece is stored at like 2 times the size of the data squared plus 19. Some random thing like that. But then we'd go to our starting point and we could just keep plugging in the size of the data. Like if we're working with 8-bit integers, we'd square 8, so 64 times 2 128, and then add 19 to that, 128, so 147. So we go to our start bit and just add 147 to get to the start of the next element, and 147 to get to the start of the element after that. And we'd keep track of it that way. That fits the definition. Pretty much anymore, it's just +1, it's the next size over. For the recursive algorithm. Back when computers first started and we had the vacuum tubes and heating coils and all that, using bits of memory like this right next to each other could be a bit of a fire hazard. So it was a lot more important back then to jump around memory so that we didn't accidentally start fires or anything. But that's not an issue. That hasn't been an issue in a long time. So anymore it's just +1, but the definition really never got changed. But the reason we can't use actual arrays in Python is this part right here of similar type. And Python is an open type language, which means we don't keep track of the type. So an algorithm like this that has the size of the data, we can't make that claim in Python. We can't say what size our data is until we actually store it. It's one of the places where open type languages are far less efficient than strictly typed languages because we don't know what we're working with until we're actually working with it.
Can you give me an example of what a language does use an array?
So most of the C family languages, so C++ or Java, whenever we set up an array, we have to say we have an array of integers. And we have to say exactly how big it is. So if we had, say, set up an array of 5 integers, in Java, those are going to be 32-bit integers. And we set aside enough space for 5 of them. So what is that? 32 times 5 is 160. So we only have 160 bits in that array to work with. And it cannot be changed. If we need like a 6th element to put in there, we'd have to make a bigger array and then copy all this over to the bigger array.
So basically, Python has just in theory, it's infinite amount, right? Until you like state it, I guess, and then like C++ and Java is like set amount. Okay.
For an actual array, because there's another data structure that I was getting ready to talk about. The one we actually use is a list, which we also have lists in other languages as well. And a list is, instead of the recursive algorithm to find the next one, a list, each element points to the next element. To the next. So with an actual array, by definition, we'd have some algorithm like this that we set up at the beginning. So we have these 5 things, and the processor is going to know where all 5 of them are right from the get-go. So we're stuck with those 5. We have to make a different version, right? But a list, we'd have the same 5 elements, and then we'd tack on just this little piece at the end, which is really just a pointer to the next element. And each one of our elements is just going to point at the next one. Just enough data to point to the next one, and then the last one just points to emptiness, just is a null pointer. It points to nothing basically. And then when the computer hits that pointer that goes to nothing, it knows it's finished. So this one is very dynamic. We could, if we wanted to add something else, we could just come in and point to something put something at that end of that last pointer. So we can grow dynamically, and we can move these things around as long as the pointer knows where it's pointing at. So when we set up a list, which we also have those in strictly typed languages as well, and it's a different type of memory usage, but it's a lot more dynamic, and we're not restricted on their size. We could have an integer down here taking up 32 bits, and the thing it points to could be a string that's 64 characters long. Does that make sense, Tom?
Yeah. I'm picking it up now.
Yeah, so there's different types of collections, and it goes on and on and on. These things in this picture, stacks and heaps, those fall in the same category as arrays and lists, and there's a long list of them. So lots of different collections that we can work with. And with all that being said, array is what we say. That's just the term we use. We actually use lists more often than arrays, but when we say the word list, especially starting in programming, people tend to think of something different, right? I just said list, you think of like a list on paper, right?
Yeah, like 1, 2, 3, 4.
Yeah, something like that. So we kind of avoid the word list unless we're specifically talking about what we're using. And at that point, we would talk about, a stack or a heap, a list, an array, a priority queue, a binary tree. There's lots of different ones. But our general catch-all term that we're going to say when we're just talking about collections in general is we say an array.
Okay.
But I just wanted to clear that up because we're going to keep saying array all through the 9th lecture. I'm going to say array, but it's actually by the technical definition, we don't have arrays in Python. What we have is lists, and lists are typically dynamic. Is one of the biggest things about them. We can change them as needed. Because well, I put marks all over here, but if we wanted to get rid of this element in an array, we would just have an empty space there. So we'd either have to move everything back a little so we wouldn't waste space in the middle of it, or set up extra instructions so that we skip over that empty space, but because we can't change it from what we started with. But with a list, if we wanted to get rid of that element, we could just take this pointer and point at the next thing, and now there's no way to reference that value because nothing points to it. So garbage collection would grab that before long. It would notice that there's no way to use that, so there's no way it's ever going to be referenced again, and then garbage collection would clean that out. Which we haven't talked about that much. It's one of the background issues, but that garbage collection is one of the main reasons that Python and Java have become so popular. They're pretty much the two most popular programming languages, because in like C++ or some of our older languages, we would have to manually do that. We'd have to keep track of that, and if we were done with something, make sure and delete it. And that can be a bit of a headache sometimes. A little bit tedious to go through and think through what's going on and keep track of all that. But Python and Java, the languages, have really, really good garbage collection. So it does all that in the background. It looks around whenever something isn't needed anymore, it clears up that space automatically for us. So we don't necessarily have to think about this a lot, especially in Python, but we want to be aware of it is the main thing. And the general picture, even though it's going to look like this, when I'm drawing it, I'll draw it like this. If we're talking about collection, it's going to be one big chunk. Because that's how we really want to think about it. And that's why where it's going to be so advantageous for us is it makes the coding a whole lot easier. Like we saw earlier, all those different reference names, we could store them all to the same reference and then just refer to them with some sort of index. And a word that showed up that's shown up before, or a couple words, countable or iterable. That really means there's a finite number of things. Kind of like this little example here of set up an array of integers in C++ or Java, the syntax there. We set up an array of integers, so there's a countable number, which doesn't necessarily mean we're going to sit down and put the numbers on them. That means we could. What countable means is there is a definite starting point and a definite ending point, so that if we wanted to, we could put numbers on them, but we are not required to. Everything we're going to look at this evening, we will use numbers to index these things, but we can also use words. And when we do that, it's called an associative array. And it can really help keep the code clean and organized, because then instead of saying like index number 4, you say like the name element in that array, and have, or name is a bad one, maybe for the employee data one, the address element in the array instead of index number 4 in the array. Makes it a whole lot easier to keep track of. But for starting out, we're just going to look at numbers. And so arrays, lists, stacks, heaps are a little more advanced. Binary trees, they're all iterable, countable. That means there's a definite starting point, and we can distinguish each separate element and eventually get to the end. So we're mostly going to look at lists because that's the main thing we use in Python. We say array. Unless we're explicitly explaining what our program is doing, what our algorithm is, even to other programmers, we're just going to say an array. And then kind of like we saw last week with, we're going to say directories, right? Even if we're talking to other people that would know what we meant when we said hierarchical database. That's just the common term to use. And the ones we're going to look at tonight explicitly is lists and tuples. And a tuple is technically a list. If we started sketching out the stack heap diagram for it, it's going to look like this without that last pointer. So it is non-dynamic. We can't change it. So it's like what the actual definition of an array is. Once we set it up, we cannot change it. You'd say we're stuck with it, but we usually use that when we want to be stuck with it for like protecting our data. Because we're humans, we make typos, right? We might accidentally add the wrong variable into the spot, and it turned out to be a variable we didn't want to change. So if we store the stuff in the tuple where we can't change it, then it's like an extra layer of protection to protect our data while we're processing. So that's our two big differences. I'm going to erase some of these pictures here and write that word on up here somewhere. Is that okay?
Yeah, that's fine.
Yeah, I guess that's not as big a deal with the everything being recorded as it is in the classroom when the notes just disappear.
Oh yeah, when I'm doing homework, I basically just have your videos up running. I watch your videos twice, basically, so I can get it down, because there's times where I just forget, right?
Yeah, it's a lot to keep track of. That is one nice thing about videos. You can pause and spread it out over the whole week instead of the lecture format. But when I tried to do everything all in pre-recorded videos, there wasn't any questions being asked. And then when I grade homework, I could tell there really should have been some questions asked. So I wanted to come back to the actual lecture part. So tuple is kind of the same thing. We'll just, for us here, I'm going to call it a non-dynamic list. And I think we're ready for the Python stuff now. Yeah, so list in Python, we use square brackets. To refer to an element or to create a list. I guess I should put that over here. So in Python, try to keep these notes somewhat organized. For a list, we use square brackets to create. And we use square brackets to index it, to retrieve the values from it. That'll make more sense when we see it in an example. Like most things in programming, it's a dynamic subject. Can talk about it for a while, but really it's when we sit down and do it that we understand it. And a tuple, we use parentheses to create it. And we still use the square brackets to index the things in it. So in both cases, we use square brackets to ask for a piece of it. If we want, say, the third thing stored in that list or that tuple, we'd ask for the third thing with square brackets. But when we create them, we use square brackets for a dynamic list or parentheses for a tuple. And the main difference between them, especially at this for what we're doing this week, getting started in programming, is that dynamic and non-dynamic thing. So a list, I'll put, that's dynamic. It can and does change on us. That's one of the most efficient things about it. I've mentioned several times Python is a very inefficient language. And list being so dynamic is one of the main ways we can buy back some of that efficiencies we lose with that makes Python so easy to work with, because it changes on the fly and we can adapt our code to maximize what it's doing constantly throughout using list. Not on this week's homework. That's more higher level. This week we're just going to throw some list out and some tuples out. And the main thing about the tuple is non-dynamic, which in regular English we have a word for that. We would say static. One's dynamic and one's static, but static means something very, very specific in programming or in computers. So we can't really say static. So tuples can't be changed. Once we create them, we have them and they stay that way. Whereas a list constantly changes. Everything about a list is set up to change. So one more stack heap diagram I want to put up here to try and cover and a point that often confuses people. Or it doesn't really confuse them. We get used to it very quickly. You've probably encountered it before, right? A lot of times in computers, we start counting at 0, not at 1. And the reason for it shows up very nicely when we're talking about list. So let's say we have some list over here with 4 different things in it. And then each one of those things is split up into a bunch of bits itself. I'll just put a couple bits there because I ran out of room very quickly. But each element, our term for is element. I can't remember if I said that at the beginning or not. Each item in an array or a list or a tuple, we refer to as an element. So each element of that, there are 2 things that show up when we're considering it. Obviously, the first one is when we ask for it. Whatever our list is, and then we'll put in some index to refer to an element of that list. And over in the memory, the CPU is keeping track of that based on the start point. So if we want the first element, we're going to go to that start point plus 0. And plus 0 elements of the array. But when we count it, is there another color I can use that'll show up? We don't really count until we get to the end, right? Because at this point we don't have any bits, so we can't consider anything about the data that's in there. So when we ask for it, we ask for the beginning. But when we count it, we count from the end. So here, we ask for 0, but we count it as 1. So there is that slight discrepancy. And then that's the same on all of them. So this second one here, we have our start point plus one element to get to it, because the computer would know each element is what, 1, 2, 3, 4, 5, 6 bits long. That's all I had room for there. So the computer knows each element is 6 bits long. So if we say the start point plus 0 element, it jumps right to the start point. If we say the start point plus 1 element, it's going to come 6 bits over and get that second one. But when we count it, that's our second element. So we have that, we have to consider the types of numbers. Cardinal numbers, the ones we actually work with, that's what we ask for in this case. Whereas the ordinal numbers, like cardinal number is 1, 2, 3, 4. We can do math with those numbers. Ordinal numbers, that's our first, second, third, fourth. Right? We can't do math with third. So there's different types of numbers. And both of them do show up. And in Python, some languages adjust for that to make it easier. And we start at 1 rather than 0. And some languages store other data in spot 0. So that we have to start at the next one. So you always have to watch the language carefully and make sure you know where to start counting your indices in the array. And they don't always line up. Like something that often happens is we're going to work with databases, and most of our programming languages, at least the most popular ones, start indexing at 0. But databases, the SQL languages, start at 1. So if we go to work with a relational database from our program, there's always that discrepancy, and we have to add one to the programming side or subtract one from the SQL side so that those indexes line up to work with. So you always have to be careful with that. And that's the reason for it, is ask for the beginning, count from the end, is the basic idea behind that. But for as in Python, we're just going to start indexing at 0. But we'll see here in a moment, when we ask for the length of an array, like if we had an array, which technically would be a list, if we ask for the length of an array with 3 elements, the computer's going to say 3. But when we ask for those elements, we'll never ask for 3. We'll ask for 0, 1, and 2. And that's something else. So I think we're ready to look at a couple examples now and see how this stuff goes together. Do you have any questions about that?
No, none any.
Okay, so let's pull up Python and look at a couple quick examples here. I'm going to go ahead and share my screen, or just some basic syntax points. The book's full of examples, and then the homework this week is going to be all about doing this stuff. And it is a very active subject. We learn by doing it. So I'm going to open a new one. And I'm going to make this smaller so that Windows 10 won't decide to put that in front of my taskbar, because that new update is driving me crazy. After decades of using Windows, I've gotten very used to using the taskbar. I don't like having things in front of it. So we'll start with a simple list. And we can go ahead and put some things in it. So like my list equals, and to indicate the list, we set up square brackets. And there's 2 ways we can do this. Actually, I'm going to add another word in. My first list, which, what's our naming convention this week? Is it Pascal case?
For last week or this week?
For this week.
I don't know, actually. I'm sorry.
Oh, There's Dustin. Let me let him in real quick. Okay, I think last week was camel case, right? I think we're on Pascal case, so I'm going to go ahead and type with Pascal case. If it's not this week, it's coming up very soon. It's just like camel case, only the first letter is capitalized as well. And that's called Pascal case. Hello, Dustin. How you doing? So we're going to start with just a simple list. I'll just throw some numbers in there.
I'm good.
I don't know, 3, 8, 27, 12, 2. Just a few random numbers in there, and notice the square brackets indicate that's an array, or sorry, that's a list. And we say array, just that's our general speaking catch-all term. So square brackets say we have a list, and there's several numbers in it, and then we can do some other things with it. Which I could probably be doing this from over in the shell. I'm gonna do this over in the shell, sorry, and just throw some points up here about this. So right off the bat, we could print that out. If we just ask for it, we get a full printout of it. And then to ask for a particular element in there, well, I guess I could do, might as well do it over here. Print my first list. That way this stuff's saved around for reference. So I'm just gonna call the print method and pass in that list. Oh, yeah, save it. Sorry, I hope that wasn't too confusing. I very briefly thought, well, maybe this might be good stuff to do in the shell, but should probably save it to keep it around for reference. So you can see we have this list and just printed out all the elements for it. And then we can do other things, like we could ask for a particular element. So that was what we were talking about a moment ago. If we want just a particular element out of there, I'll just put it in a print statement. So print the third element is plus that list, my first list. And then our third element will be, we start at 0, so that's going to be index number 2. So 0, 1, 2. So remember, ask for the beginning, count from the end, which is a number, so we need to cast that into a string to print it. So now when we run it, well, the first line printed out the whole list, or you can see we grabbed the third element right from the list, and then that difference between cardinal and ordinal numbers. Third is an order. It defines ordinal number. It defines the order something goes in, the order that thing came in the list. Whereas the cardinal number, what we would need to work with is the 2, the actual index that we're asking for. So we just have to watch those two things. Let's see. We can get the length of a list. The list has length plus length of my first list. And it looks a lot like our casting methods. That's when we cast something into a string, we just have that 3-letter abbreviation, and then the thing we want to turn into a string. Length is very similar, just an abbreviation for it. So just LEN, and then the list we want the abbreviation of, which the length of a list is going to be a number. So again, we have to cast that into a string to actually put it in a sentence like this. So save that, run that. And you can see it gives us the ordinal numbers, the order that they go in, which is first, second, third, fourth, fifth. So we have our last thing is the fifth element, but it has index number 4. And we can add things to a list. That was the biggest thing up there. The main thing this week when we choose which one to use is our lists are dynamic. That means we can change them. Everything about them can be changed as needed, whereas a tuple is non-dynamic. Once we set it, we can't go back and modify it, which makes it nice to predict it, nice to protect our data. If we take away that ability from ourselves to change the values that we know we don't want to change and prevent accidents from happening. If we can add things to that list, so like my first list dot append is the method to add stuff. And notice here, this list is all numbers. That's another thing like we were talking about earlier. It's gone from the board now in some of the strictly typed languages, and to fit the actual definition of an array, we can't mix the types of things. But with a list, we can, because the list just has instead of that recursive algorithm that is going to have to know how big each element of stored in it is, a list just has a pointer to the next element. So we can point to the next thing any way we want to. So that's what here in the prediction, it just says object. Even though we have ints, we can add anything we want to. Obviously, it's a list of integers. So, in most cases, we're going to add another integer to a list of integers because we organize things like that. That's what we're going to use this for, is organizing our code and preventing things like that first example where on a payroll calculator, we have a whole lot of variables that look very similar, right? Employee 1 name, employee 2 name, employee 3 name, and so all those variables kind of blend together. So it'd be nice just to refer to them all as a collection. So we're going to, for organizing it, we're going to keep our data the same, but that's not a restriction. We can add a couple other things. So dot append some string in here, some random words, or a Boolean in here. 3 less than 5. I don't think that one's going to crash. It might cause a problem in idle. We'll see. Oh, whoops. I forgot to print the list out again. That's probably an important step here. Print adding some items. And then print my list. You can see it just tacked those right on the end. And our basic syntax for a tuple is going to look very similar when we set it up. And when we ask for things from it, the difference is when we create it, we want to use parentheses to create it. And then obviously we don't have an append method. We can't add stuff to it. Oh, before we get into tuples, just like adding things, we can remove things. Might as well do that somewhere. So like my first list dot remove, and then we have a couple options. Notice it says value. So what do you think goes in that value? Not quite sure.
No, yeah.
I heard the mic come on, so let's try 2 and see what that does. Because that's the best way to learn. Just try stuff and see what happens, right? So let's throw in a 2 because we have an index number 2 index number 2 is 27, or we do have a 2 in the list. And we can just give that a try and see which one it takes out of there. Print removing stuff, a little label, and then print my first list again.
I'm going to guess that it takes out the second, like not the actual number 2, but the second. Oh, wow. Never mind. It does. Okay.
It took out the value. Yes. So remove, we have to specifically say what we're removing. We could try that. Let's try that again and see if it does it that way. Right? My first list, remove 2. Maybe it just does that first and the other one second. Well, there's not a 2 in the list. Which, going back to last week's thing, if we wanted to try catch block, we would need to catch, we'd look for a value error. So remove actually takes out that element. If we wanted to remove that second thing, we know it's the second item in the list, right? So one way we could get to that value is by actually requesting it from the list. So if we just want to actually remove the second item, we just type it out like that.
And I can't really tell because I have bad eyes, I guess. It's the brackets, right? Not parentheses.
Yes, square brackets. This is why I usually use Notepad++ in classes, because it has a zoom function. Most text editors don't give us a zoom function. Maybe bigger than that. How big is that? What? Is that better?
Yep, works for me. Definitely.
Okay. Yeah, I usually, there are much better text editors, but I tend to use Notepad++ in class a lot of times because it's the only one that seems to have a zoom function on it. A lot of the text editors won't even let you resize it. It's just kind of a save thing. So yes, square brackets to index ask for a particular one. And then the parentheses here just go with that function, with the remove function. So now if we run that, oh good, it made that big too. You can see we got both elements out. So the first time through, it went through and saw there was a 2 in there. So it removed the actual value 2 from the list. And then the second one, we actually wanted the second, the third element, so index number 2 removed. So it went in and removed the third index from the list. And that's the power of lists. We can change, we can add stuff to them, we can take stuff out. We could check things, remember it threw a value error before we did that, right? Or when there wasn't a 2 to remove. My first list dot contains. Nope, not contains, nothing showed up in the thing. There's a keyword that'll let us show for that. But this is the point we haven't really done so far. Is you want to check the reference material. And right, we have the book, but one of your top sources here is one you've probably seen in other courses as well. If we search for something about Python, so list has an element in Python, one of the results should be the W3 schools. Check if element is so there's a pointer thing. There's some good sites, Geeks for Geeks. That site always has really thorough explanations. And so does Tutorials Point. Well, I was expecting W3 schools to be near the top there. I'll add it on there. W3 schools. Is it like a lot of things that's Python is one of our server-side scripting languages for website stuff, so it kind of fits on theirs. And when you go through here, you'll be able to see all of the different things we have. So like the link, we saw that. We'll talk about the types, example. Yeah, if we ask what type it is, it's just going to say it's a list. Oh, here it is. Access list item. So here's a long list of things we can do. Access the items, change list items, add list items, remove, sort list, copy list, join list, list methods, list exercises. So there doesn't seem to be something that explicitly says it contains a particular element, right? So we might have to write that ourselves. We can always write our own methods. We've seen that a lot. So I'm going to come up here to the top and define a new function like we saw last week, called contains. And to this, I'll just pass in something called L for a list. And that shouldn't be too hard to tell if that element is in there or not, right? So we'll pass in the list. I kind of want to spell that out, but it's not going to let me do list as I'll put my list. That way it's more explicit and clear what it is. So in order to check the list, we'll need two things, right? The list we're going to check and the value we want to check for. And then we can just walk through that list with a for loop, because that it's not wrote on the board anymore. Lists and arrays, collections in general, one of the aspects about them is they are countable or iterable, which means there is a definite starting point and a definite ending point. And that's what the for loops in Python are like designed for. In every other language, what a for loop in Python is, we call a for each loop. And it kind of makes more sense to think of it that way. So like for each thing in that list we passed in, we can just check and see if it equals the value. If thing is equal to the value we're checking against, we'll return true. Oops. But if it's not, we can just return false. Everything in the logic there makes sense.
Yeah.
Should be kind of an easy one to work with, right? And well, you saw how long it took to just get to the W3 sites and scroll around. For simple things, sometimes it's easier just to write your own method, because if you named it, you're never going to forget the name. You're going to have to go look it back up. So now it's not something about the list itself, but we did add this contains method in, so we can check and see if my first list contains the number 2 before we remove it. And then that returns true or false, right? So since that's a true or false, that's a condition we can check. We actually want that in an if block. So if my first list contains the number 2, then remove the number. And that way we don't have to worry about a type error, right? Without the error, the value error. We don't have to worry about throwing a value error, because we can check and see if it's contained in there first. You always want to think of something like that. Like last week we saw the try-catch blocks. So we could put a try-catch block and then a round match, and then it just wouldn't, whenever it couldn't remove that, it just wouldn't do so. But it would also halt the execution of our program. This way it keeps going, and there's different ways to deal with errors, but whenever we go to do things like that, especially take away stuff from the list, we want to put in some precautionary things. Make sure that number is there before we go and take it away. Whoops. We're in Python. Capital T and F. I do that all the time. Almost 15 years of using Python now, and I still put lowercase and uppercase letters there all the time. Which, when we get to tuples, that's the main thing of that protection issue. It protects our data from us making a typo, because as humans, we will. So might as well add another thing here, an else statement, and print that value is not in the list. If it is there, we'll print removing the number 2. Just a couple labels to help clear up what is going on there. Now when we run it, wait, why didn't it say that? It should have said the other thing, right? I must have got a typo while I was talking. So pass in this, return true. That's actually say equals true. Oh, I know what happened. We don't want to return false every time through that loop, right? Because our first element was not a 2. It got to that 3. Well, 3 is not a 2, so it returns false, and then it's done with our loop. So we don't actually need an else here. We want to go through all the way through our loop, and we'll just return true and exit this loop altogether if we find that number. And then we only return false if we don't find the number. Does that make sense? Kind of see what went wrong there? And that's...
Yeah, why don't you have to have else there?
Yeah, so that's that.
Oh, okay. So this is what's called, so for desk checking. So here's what it was originally. And it's returning the wrong numbers. So we need to go through here and see what's happening. So our first number, whoops, those are in the way. So our first time through, our thing is equal to 3 and value equals 2, right? So those are not equal. So that's the very first element on the list. That's supposed to be a T here. It looks like a plus sign. Maybe I could have done uppercase T. Sorry, that's a T for thing. But our first element, our first thing is 3, and our value is 2, so those are not equal. So it's going to go in this else block, right?
Right.
And then it returns false, and return, as soon as we hit the keyword return, we go back to where we came from. So we're done with that method altogether when we hit the return. So then it's not going to go any further in the loop.
Right.
Does that clear it up?
And I think so. I guess I have to look at it again. I don't know.
Here, let me write these down. So let's say our first element was a 2.
Right.
So then we pass in the list and we pass in the number 2. And in that case, thing, because it's going each element in that array that we're calling it thing on our way through. Each thing in the array, the first thing is the number 2. And then we're comparing that to the number 2. So that's true. So then we hit return, and return goes with our function. That means we're done with the function.
Right.
So when we hit this line that says return, we're finished, and we come back down here to where we came from, which was where was that? Oh, there it is. So we come all the way back down to past it. Then we come right back down to here. And we're going to say, and now this has a value of true. Does that make sense?
Yeah, I think so.
So then, whoops, I'm going to hit the clear button and hit the close button. Clear all that. So but our first element here is a 3, not a 2. So then when it gets down to make this comparison, it's going to say 3 equal to 2.
False.
Which is false. So then we'll take the else block, and when this keyword return means go back to where we came from.
Okay.
So I guess
that's going to jump
the thing is, like, I think that
back
maybe
down here.
he might have been asking close to the same thing, but like, so if you take out the else, does it just run through everything, checking everything, and then at the end it just returns a false and leaves?
Yeah.
Oh, whoops. I clicked the wrong button. Not necessarily, because if we take out the else, let me make sure I cleared all my pictures. If we take out the else, then afterwards, I'm going to put the word return false here at the end. And I already spelled it wrong again. Here we're going to go through our list again. Where'd my little pen go? So the first thing is a 3, which 3 does not equal 2. So we don't go in this if block at all, and we come back around our loop, right? Then we check an 8, and again, thing does not equal 2, so we don't go into our if statement and just come back around the loop. Same thing for 27 and 12. None of those are equal to 2, so we just keep coming back around and going through the loop without doing anything.
Okay.
Thus far, our loop hasn't done anything. Does that make sense?
Yeah, I think I
And
got
then on
it.
the last one, on the last one, 2 is equal to 2. So at that point, we were returning true back down to that condition down there. But
then it goes
if
to
there
false.
wasn't a 2 there, if it went all the way through the list, once it ends the loop, well, it hasn't returned anything. So then it's still inside the method. And after the loop, the next thing to do is return false.
Got it. Okay, now I understand it.
Yeah. Makes sense.
Yeah, sometimes it's a little complicated. So this kind of is an if else. We're just doing lots of ifs, and then only one else. The only way we're going to return false is if we hit the end of the list. Anything else we're going to leave early. And we don't have to explicitly state equal to true. It can be a good idea to. It helps to keep our code cleaner. But this right here, well, since 2 is in the list, that's going to return true. But if we ask for a number that is not in the list, that'll return false.
Got it. So basically, one just feeds into itself, and the other one, as soon as it doesn't see it, it exits out, right? Am I kind of getting that?
Yes.
Got it. Okay, yeah, I got it.
Yeah, one of them, that if block catches anything, we're done. It's like the word break. We could have used the words break and continue. And if it was like a void and we weren't actually sending anything back, we would need to use the words continue to jump out of the if block and then break to jump out of the loop. No, I said that backwards. Break to jump out of the if block and then the word continue to jump out of the loop. But with return, that does both parts. It goes back to where we came from. And that gives us a little bit of protection so we don't get that value error from trying to remove a number that doesn't exist. So you want to keep things like that in mind. And notice it's really not that hard to just throw that little method together. And once you do something like that once, you never really have to do it again, right? We could just save that into a file. We'd want to be careful with all of this because all of this stuff's going to run. But this method itself isn't going to run until we ask for it. So we could just put that in a file and then call that a module and import that module and use that anytime we're dealing with list. It's just a quick check to see if that's there. And I like to do that. That's what all these libraries that we have to work with have come from. Programmers, as they need things, they put them together and then just kind of put them on places like GitHub and stuff like that where other programmers can use it, and then they don't have to write that same method. And over time, you build up a large library. So it's kind of nice. It's very nice to have access to all those libraries that have already been written, and we don't have to write this stuff. But when you write your own, especially for people that are going to be software developers, going specifically into the field, and will be programming all the time, if you write your own library, you don't have to worry about memorizing what somebody else called it, because the names of all the methods and things are going to be what you call them, which makes it a whole lot easier to remember than trying to remember what somebody else did. So that's just some basic points about lists. The book has quite a few examples. Excuse me. We look at tuples. They're going to be very similar, except obviously tuples are non-dynamic. So we don't have this append and remove stuff. Those are the ones we don't have. Because we can change something. I'll just make up another example. My tuple equals in parentheses, and then in parentheses, we pass in the stuff we want it to hold. So maybe like 5, 4, 8. It's got those 3 numbers. So obviously we can just print that out. And I'm going to comment out all that list stuff. Is that okay? Highlight all this. That way, because our print lines have gotten kind of long. Well, before I highlight that first part, so I'm going to highlight that and hit Alt-3 to comment on all of that. Before I highlight this, is there any reason that wouldn't work with a tuple? We haven't really looked at them yet, but we kind of index them the same way, right? It's a collection, so we can walk right through it. We can start at the beginning, go to the end, and we could compare it to every single value. The difference really is when we brought that back, we can't remove things from a tuple. We could replace it with a 0 maybe, but we couldn't bring it back in order to remove that element, but we could still use that to see if it's there. So a lot of our methods are interchangeable like that, and you want to often stop and take a second to think about whether it's going to work or not. So here, if we print that out, we just like the first time, but you see when it prints out, we get the parentheses around it to indicate it's a tuple rather than a list. And then there's those things, so we can access it. So print the second thing, print. So how am I going to ask for the second thing in this my tuple here? He's not. So accessing it, we access it the same way. When we access it, we have to access it by square brackets. Because accessing things with parentheses means a function or a method like we were looking at last week. So we would still access it from the square brackets. And then the second thing, we start at 0. So first thing's index 0. The second thing will be index 1.
So that would print out the, wait.
Does that confuse you?
Why didn't it print out the 5? I'm sorry. I guess I'm having like a tough time remembering.
0 value.
Oh, 0 is the one. Got it. Okay, yeah.
Yeah, 0
sorry.
first.
Yes,
So
sorry.
start at 0 and ask for it's in that picture on the board. So to get to the 5, we have to ask for 0 because we go to the start point and don't add anything to it. But to get to the 4, we go to the start point and move, and then +1, so moving past that 5 in order to get to the second thing in the list.
Yeah, sorry. I guess I just keep. It's hard for me to put that in my head that 0 is equals 1 and then 1 is 2, and
yeah. Another way that I've heard it stated that some people like better is when we're counting. If we start counting at 1, we have to do something to get there, right? Because nothing to get from 0 to 1, we have to do something.
you have to add 1, right?
Yeah. So if we start counting at 1, we have to do something before we count. So you can think of that as, to make it easier, we don't do anything before we start counting. So we start at 0, and it'll just take a little bit of practice.
Yeah, the way I gotta think about it is like 0 is a starting point. I just gotta think about it that way.
Yes. 0. Think of starting at 0, and it'll you still get thrown off sometimes, and it'll be different in other languages too, which makes it even more confusing. So
great.
just run test cases, run simple test cases, and make sure you remember it. But everything we do in Python, all your homework this week, start at 0. And maybe just while you're doing things, going about your daily life, right? Try counting at 0, right? If you go to the Dollar Tree and they say it's going to be $4, start counting at 0 just to practice it. And the fourth dollar would be the 0, 1, 2, 3, and kind of get used to it. It does take some practice though, but you'll get plenty of practice with that in the homework, and you'll be quite used to it afterwards. What's some other things? Oh, I'm going to come over here and write something about this right in here. We saw this when we were looking at for loops before. The book really liked this, right? Range from say 1 to 10. And when we return that, x equals range 1 to 10. And now if I print out x, it's trying to bring back the function. Can I say print x? Nope, it's just printing the function. I was expecting it to return the tuple. That's what that is, right? All the numbers from 1 to 10 right in order. I was expecting it to print out the tuple. I'm going to close that to kind of clear out some space. So we can access it the same. Print, try to add stuff. Well, I'll modify stuff first because that can work. Modify stuff. So my tuple element 1 equals, let's make it a 9. Now print my tuple again. So what do you think is going to happen here? Any thoughts? Is it going to crash? Going to replace that?
I say an error's going to come out, right? I don't know. Maybe not.
Oh, hit save and run it. And again, yeah, the best thing to do is check when you have questions, but guys,
Yeah.
It's non-dynamic. We said our tuple contains 5, 4, and 8, and that means our tuple contains 5, 4, and 8. So then at some point, if we meant to say, well, like in this script here, we have my list and my tuple. If we were meant to say my list element 1 equals 9, accidentally type my tuple element 1 equals 9, it's not going to change it. So we have, it protects our data. You can think of that's when we'll want to use it. We don't block ourselves from making a typo or a little mistake like that. So we can't change those. So that, I'll comment those out and add in a comment here that says does not work. Then there's some other stuff we can do.
This is just like thinking ahead, but basically the idea of importing data like over time, like let's say you have like a program, like, keeping track of purchases throughout the day. You just basically have that array going through a loop to add one number on it and then plugging in the data into the document that way.
Mm-hmm.
Okay, I see.
Yeah. So for that, you'd want to use a list because you can keep adding stuff to a list.
Okay.
You'd probably start it with, like in that case, maybe it's called daily sales. And we'd start it as an empty list with square brackets instead of parentheses. And then, after the first sale, daily sales plus equals 5. Whoops. I have no idea what I was just thinking there. I think it's time for a break. It's a list. So daily sales dot append 5. Oh wait, I know what I was thinking of. I was doing PowerShell stuff earlier today, and in PowerShell we can use plus equals for arrays, which is really nice because then we just use our regular add to it. So maybe our first sale is 5, then we add a 5 to that. And then later on, the next customer comes in and spends $15. And just keep adding them like that. Is that what you were talking about, Dustin?
Well, kind of like yeah, pretty much like a loop basically that just automatically adds +1 to the number of the array. So you have like whatever array number it is +1, like
to
array
walk
plus
through
itself essentially. That's why I was just thinking like is that pretty much like the future, what we're going to be doing in like future lessons. I was kind of like thinking ahead just to kind of like understand where this is going.
So that's what a for loop does automatically in the background. It does it without the numbers. I think we talked about it right before you came in. The numbers are not a restriction on us. We could index these by words instead of numbers.
Got it. Okay.
We're not going to see that in this class. That's called an associative array, but the numbers aren't necessarily a restriction. But that is the typical thing we would do, is we would do a for loop that goes through our array and just looks at each one. And the for loops in Python, so in other languages, our for loops would look something like this. So like in Java, we'd have integer I equals a 0, go for till I is less than the length of our array, then increment I, and that's what you're talking about, right? So we start at 0 and just go through the entire length of that array and just look at them one number at a time.
Yep. Okay.
Yes. So that is what it is in most languages. And in Python, they abbreviated it because we don't really need the numbers. So in every other language, we also have another loop called for each. So for each I in our array, it would look something like that. And does it make sense how those two syntaxes are doing the same thing?
Yep.
One's using numbers, starts at 0, and 1, 2, 3, 4, 5, however far it is. And this kind of does the same thing. So we'd start at 0, and then 0, and then the for part means it's going to go 1, 2, 3, 4, 5, and go through every single one. So it's like those numbers are included for us in Python. So we don't have to worry about the numbers. We can just say for and however many much. I hope that didn't make it more confusing there. But what you were saying, that is what we use for loops for. Yeah, so we can append stuff to an array here. But if we try to append stuff to a tuple, this is going to cause a problem, right? Because once again, there's that non-dynamic thing. Tuple has no attribute append. We cannot append something to a tuple. Was there a 5 in there? Yeah, there was a 5. So we did the same thing with remove. If we try to remove something, we can't take it out. So tuples help prevent accidents. We can't accidentally remove a 5 from our collection here. We can't add a 4th element to our collection that should only have 3 things. So think of the tuples for like protecting things. And I know it's time for a break. I want to do one more thing just because it goes with this. And while it's fresh on our minds, I'm going to put another function here. Define double, and we'll take in some number. I think this exact one, I want multiple returns, double or half. So we'll take in some number and then return x times 2 or x divided by 2. So we can do that. We can do multiple returns, right? And I'll go ahead and run this and just call it from the shell. So if I call that method now, so double or half with a 4, what we saw before, we would put that in 2 things, right? We'd say x comma y equals that because we know it's sending back 2 values. And then we can print out x and we can print out y separately. But I just wanted to look at the return type on those. Double or half the number 4. And so now you should recognize what the return type is, right? Is that a list or a tuple? So we look at our symbols here. Do you remember which symbols we use for a list?
I believe that's the list, right?
The other way. The square brackets are a list. let me go uncomment all that stuff so we can close this, and I'll print all that stuff out on list so we can point at them again. That way they're both on the screen. Alt-4 to uncomment that. I'll run that again. So here was the stuff about list. Right? And notice we have the square brackets and square brackets, square brackets. But then when we get down to tuples here, we have parentheses. And that's what we get from that those multiple return functions. Say an 8. So we doubled it and halved it. So we had 2 returns, but notice it's a tuple, not a list. Which is another, I was hoping would help make sense of times we would want to use a tuple instead of a list. Because this function returns 2 values, right? So whatever number we pass in, we're going to get 2 numbers back. So no matter what, if we're dealing with the result, with results that came from that function, we always want that to be 2 elements long. We don't want to add a 3rd or 4th element to it, and then at some point later try to figure out what was the actual return from that function. I was hoping that would help make sense of a place why we would want to use that non-dynamic structure when it seems like lists are so much more powerful. 99% of the time, we're just going to use a list because they're very dynamic. We have a lot of control over them. We can put more stuff in, take stuff out, and indicate that. The big thing to keep track of, take note of, is for a list is square brackets, and for a tuple is the parentheses. So if you see parentheses, it's a tuple. If you see square brackets, it's a list. And in our code, we use those symbols when creating this. And I think I erased that example, that quick one I put there on daily sales, where I started with just empty square brackets and then added just some stuff afterwards. And then the tuple, we create that with parentheses, but on both of them, we use square brackets when we ask for an element. Does all that make sense?
Yep.
Okay, so I meant to take a break about 10 minutes ago. So why don't we go ahead and take a 10-minute break, and then there's just two other things that I had on my list for talking about list, dealing with these. We'll talk about those real quick, and then address that issue you asked about last week, Dustin, and see how to do that.
Okay, sounds good.
So let's take a 10-minute break, and I will see you all at 7:40.
Alrighty, I'll be right back.
So real quick, this doesn't have to do with anything right now, but on my homework, I